So before starting this presentation, I wanted to say a few words about the projects that have been presented at Giens. So of course, our science drivers can be performed, as it has been said also by Iulian, on our national facilities, but not only, and in an important part, especially concerning what we call the reaction spectroscopy part, can only be partially done at Ganil and required to work on international facilities. So at this point has been also pointed out in the final document written after our town meeting in Caen. I think, if I remember right, it was in March 19. And therefore, the idea was to focus in Giens on our national facilities, not because they are the only one we are interested in, but because we need our tutors to support it, and because since the first phase of Spiral 2 is now slowly entering in the exploitation phase, it is now time to think about the future of our national facilities. So this is the main reason why in this presentation, I've divided my talk in two parts. First, indeed devoted to the development of our national installation, with three parts: where we are right now, where we are going in the near future, but which is already on the way, and where we could go as a next step. And in a second part, which will be a bit shorter, I wanted just to give some example of project of R&D that we are developing in our labs for both reaction spectroscopy experiments and stop beam experiments. So maybe just for our young colleagues, just to remind you that, as it has been explained by Iulian just before, our science driver require that we can work with different nuclei which are located on different parts of the chart of the nuclei, and that these different nuclei require different techniques to be produced, as it is highlighted here with the circle of different colors. And basically, if we want really to be really schematic, there are two ways to produce this exotic nuclei: what we call the in-flight method. Maybe I can put the pointer. You see my mouse?
Yes.
Yeah.
Yeah, we see it.
Okay, I don't know how to put it in red, but okay. So there is the in-flight method, where you produce the nuclei in a thin target, and you study this nuclei with what we call fast beam experiment. And we have the isol method, which consists in using a third target, and then we produce this exotic nuclei nearly at rest, and we use them in what we call the stop beam experiment. And to give some schematic behavior, basically with the in-flight method, you produce more exotic nuclei, but in lower quantities. And with the isol method, you produce more nuclei, but a bit less exotic. But of course, both of them can be mixed, because you can also stop the ions which have been produced in flight to make a stop beam experiment, and you can also post-accelerate nuclei which have been produced by the isol method. And concerning the adequation between these methods and the science driver, basically there is no one-to-one connection. And the idea of this slide is to say that for all our science driver, we need nuclei which are produced by these different methods. And somehow we are using what we call the holistic approach, or to be more, using words which are used at Untitled in different communities. We are using a kind of multi-message approach. And concerning our national facilities, you can see here that basically they cover all the different possibilities. So I will start with the national platform, which is ALTO. So at ALTO, there are two different accelerators, 15 megavolt tandem, which allow to accelerate stable ions, to make nuclear reactions and decay, or to produce also neutron beams using the device LICORN. And there is an electron accelerator, a LINAC, which is used to produce exotic nuclei, mainly fission fragments by the photofission of a uranium target. And so this facility is part of our recommendation, since I remember that the recommendation 6 is to increase the beam time at Alto and Ganil. And also, in order to go in this direction, you can see that there are still upgrades ongoing at Alto, and here is just to show you a kind of innovative method in order to extract pure beams. And in this case, the tin isotopes are extracted as a molecule with a sulfur, and then it allows to completely remove the main contaminant, which is antimony. And you can see here that the blue one is when you extract directly the mass 133, where the red curve, it's when you extract the molecule done with a sulfur, and then you suppress completely antimony, which does not form a molecule with the sulfur. So by this way, you can get more pure beams, and then also to increase intensity because we concentrate on the nucleus of interest. Concerning Ganil, it's our TGIR, Très Grande Infrastructure de Recherche. For the historical Ganil, we have beams which are accelerated by several cyclotrons. So either you use only one of the big cyclotrons and you accelerate stable beams up to few MeV per nucleon, and then you can make nuclear reactions basically at the Coulomb barrier. It's what is done mainly with VAMOS, which is represented here. Or you can accelerate the beams with the two big cyclotrons in addition to the smaller ones. Then you can accelerate the stable ions up to 95 MeV per nucleon for the carbon. Then either you can make nuclear reactions at the Fermi energies. It's typically what it's done with Indoraphasia. Or you can use these accelerated AV ions to produce exotic nuclei by fragmentation, either in flight, as I was saying in the introduction, using the LIS spectrometer, or with the ISOL method, using the spiral device, which is located here. So this is our Ganil right now. And also on this historical part of Ganil, there are some work ongoing, some upgrades, we can say. And for example, the spiral 1 source has been changed drastically in the last years to move to a Febiad ion source. And the idea was to increase the variety of beam that can be delivered by spiral 1. And you can see the comparison here in this figure between the use of the previous nanogan ion source and the Febiad one. And this could be also continuing in the next year to again enlarge the range of possible nuclei. But I mean, these are just pictures, and you have to keep in mind that these developments are very time consuming, and that basically in order to produce a single new beam, you need something like 1 year of development. So it's not really, it's not straightforward. So now, what are the strengths of Ganil as it was for many, many years and as it is now? So we can say that Ganil LIS is still unique for the study of direct reaction of exotic nuclei, mainly because the energy range is really adapted to some reaction. And Ganil VAMOS on one side and Ganil Indoraphasia on the other side at different energies are kind of state-of-the-art devices for their domain of expertise. And as I said in the introduction, and as it has been said also by Iulian, I mean, our scientific programs, we all know that they should be also performed on international facility. So GSI, FAIR, Weekend, Dubna, Tomorrow Space for the in-flight program, ISOL, Gvascula, Triumph for the stop beam program. So now, where do we go in the next few years? As you know, now since 20 years almost, the French community made the choice to move on toward the ISOL method in order to really develop the ISOL method at Ganil. And then this was what we called the Spiral 2 project. And the Spiral 2 project at the origin was thought as the first step toward the ultimate facility, namely the URISOL project. So right now, almost the phase 1 of Spiral 2 is almost completed. So Spiral 2 is based on a LINAC accelerator, able to accelerate very, very intense beams. So from very light nuclei, proton, deuterium, alphas, up to heavy ions. And you have on the right, basically the last news about the commissioning of Spiral 2 LINAC. It's not really anymore a commissioning, because now it's working for at least for some beams, it's working at nominal specification for proton, deuterium, and alpha. And for the heavy ions, the first extraction have been done up to nickel, and the first oxygen beam has been accelerated. So really now the accelerator is working. And the idea is to use in this first phase the proton or deuteron in order to produce neutrons to be used in NFS, neutron for science. And this room is ready, and first experiments have been done already in 2020 and 2021, so this year. And the heavy ions, they will be used in the near future within the F3 cave in order to produce exotic nuclei, mainly heavy and super heavy nuclei by fusion evaporation. And this mainly proton-rich or super heavy nuclei, they will be studied either at the focal plane of S-cube here, or transfer to the DESI hall that is also part of the Spiral 1, phase 1 of the Spiral 2 project. So now in the next 3 slides, I will come back a bit more on detail on the 3 projects which are still ongoing. Yes, and I forgot to say that for the LINAC itself is now delivering beams, but there is a new project that started in 2020, so last year, in order to have a new ion source able to accelerate really even more intense beams than what would be possible without this new gain source. So first, the S-cube spectrometer, which is located here just after the LINAC. So the aim of the S-cube spectrometer is to perform the physics of rare events. And then you need to produce large quantity of N=Z and super heavy nuclei by fusion evaporation. And then in order to do physics, you need a spectrometer able to have a high transmission, high rejection capabilities, and also a mass separation feature, which makes this spectrometer quite unique in the world. So concerning the science drivers that have been presented by Iulian, you can see that S-cube will allow to access not only one, but few science drivers. Concerning the technological challenges that exist in such a project, there are many, of course, but we can say a few words about the high intensity targets. Of course, when you have very intense beams, you need target able to sustain such intensities. So huge work has been done on this part. You need also to stop the beam that you are not interested in. and then you need high power beam dumps. And for example, you have one in S-Cube with movable stoppers that should accept up to 1 kilowatt per square centimeter. It is really a colossal power. And you need, of course, optical elements, which are quite innovative. Here we are talking about supraconducting multiple triplets, because you need both a high transmission and high rejection. And usually these two things are difficult to get together. So in order to have both, you need really to work on the magnetic, on the optical elements, and it is done this way. And concerning the status, the timeline and investment of this project, most of you know that we are in the final phase, and the commissioning is expected to start basically in 1 year or 2 years from now, 2 years. And the day one experiment is scheduled for beginning of 2024. And of course, as you can see, there are huge investments for such a project. And S-Cube has been supported by an Equipex and also a lot by the region Normandy. So the second project, which is still ongoing on this Spiral 2 phase 1 part, is DESIR. So DESIR is the low energy ore of the Spiral 2 project. So it can be seen as a kind of isolated hole for DESIR, for Spiral 2. So the science drivers are basically the same as the one of S-Cube, but S-Cube in DESIR, you will also have the Spiral 1 beam that can be sent from the target station of Spiral 1 here towards DESIR. So you have even larger physics case. And basically, you can say that in DESIR, we will make decay spectroscopy experiments, sharp-assisted spectroscopy, and laser spectroscopy experiments. So the technological challenge in such project, in fact, in DESIR, the key word is precision. We will perform precision experiment, and then when you want to make precision experiment, what you need is high purity for the secondary beams. And then the technological challenge are in developing all the purity setups, such as the HRS, the GPIB, or P prime. And just to illustrate that, here you have an illustration of the aberration that have to be corrected at very high order in order to be able to really have a mass resolving power in your separator, which is enough to separate all the contaminants. End the status and timeline, I mean, the building is expected to be built starting in end of 23, 24 for the first experiment with radioactive beams in 2027. And concerning the investments, here again, they are quite huge, and an Equipex has been also obtained for this project. So the third project, which is still existing as a project in the Spiral 2 phase 1, is new gain. So new gain for new GaNIL injector for A over Q equals 7 for the LINAC. So here the idea is to enhance the physics program of S-Cube and DESIR by providing basically the worldwide highest stable beams intensities, and also so this is to produce at the end more exotic nuclei, but there are also some possibilities with such a new injector to be able to accelerate very heavy beams like uranium, and then why not to open new possibilities to produce exotic nuclei by multinucleon transfer, for example. So on this table, you have a comparison of the stable beams that will be accelerated. So this is in particle microamp with new gain in the LINAC, and you can see that compared to what is accessible the best in the world, new gain is really give an advantage for some of these beams. And of course, the net result is that more intensity at the entrance of S cube means more production of exotic nuclei. And you can see here the production of some very heavy nuclei on the n equals z line with new gain and S cube as compared with F rib in its final configuration. So here again, you have some technological challenges concerning the source, which is superconducting, which has to be optimized for metallic beams, and also concerning the RFQ, you have some challenges concerning the radio frequency fields and the length of the system. So status, it's the project, as I said, just started last year. So the construction is expected to be in between 2023 and 2027. And here again, as you can see, another Equipex covering almost all the project has been obtained. So this is for what is, I would say, already ongoing. So this will come in the next 3 to 5 years, I would say. So now, what are the possible steps behind this? So I remind you, as I said also at the beginning, that the main objective of the Spiral 2 project was to build a world-class facility able to produce and post-accelerate large quantities of fission fragments. And since now the phase 1 of Spiral 2 and not the phase 2 of Spiral 1, as I said in Giens, is starting its exploitation phase, it's time now to propose new developments for our national facility. And this work somehow has been done in collaboration. Hope Yorick is not here, but has been done in collaboration with the Mission Spiro. So we have mainly 3 recommendations, which are recommendation 5 and 8 in our final document. First is to enlarge the range of isol beam available at Ganil, going back to the original project, which was to deliver fission fragments, and also new opportunities, as I said, with maybe these multinucleon transfer reactions, to take advantage of the French expertise on the in-beam studies, having post-accelerated secondary beams at energies higher than SIM, and to prepare the far future with an innovative project, and namely to look at the possibilities to make collision between radioactive ions and electrons. So basically to use the electron as a probe for the exotic nuclei. So I start with the fission fragments. So this means that we would like to have a production at a building at Ganil, as it was foreseen in the Spiral 2 project. This, of course, will increase the physics program of the DESIR Hall. I remind you that at the beginning, the DESIR Hall was thought as mandatory for to study the fission fragments produced in this production building. And then also taking, I mean, we learned a lot also from ALTO in the last 10 to 15 years. And now what we propose is based on this experience to have a dedicated driver to produce these fission fragments using a beam of electrons, as it is done at ALTO, but using a commercial electron driver, which could be, for example, a rhodotron. So, of course, the number of fissions at the end, the total number of fissions will not be as high as what we could have imagined in the beginning of the Spiral 2 project using the most intense deuteron beam, but because, in particular, because you can use smaller targets. If you look at the most exotic isotopes, basically the rates that you can have with such a system will be or could be equivalent. And it will be much faster to build than the original phase 2 of Spiral 2. Okay, so as I said, the idea was to use a commercial electron driver. And as you can see here, already a few studies have been done to see what could be proposed exactly. And then such a system would allow also to use the beams from the LINAC, and in particular the heavy ions, in order to produce other nuclei using the multi-nucleon transfer reactions, so nuclei around n equal 126 or in the super heavy region, but also light neutron-rich nuclei. So basically, with this scheme, somehow we gain in coherence for a multi-user facility, because mainly we could have a program both in S-cube using, for example, the fusion evaporation reaction produced thanks to the beam of the LINAC, and in parallel, a physics program in DESIR made on the fission fragments produced with the electron driver. So it's really a parallel operation of GANIL, which will be interesting for the community. So I try to move a bit further and faster. So the second point, the second proposition is to look at the possibilities to post-accelerate these exotic beams produced in the production building. Indeed, as I said, we have a large physics program as presented by Iulian, based on fast beam experiments, so in-beam spectroscopy, nuclear reaction mechanism. We have a long-standing French expertise on these fields, and it's maybe not the smallest argument. There are existing and ongoing developments on very powerful detectors like the one which are written here. And in the following, I will just give a few words about Agatha and Gray. And also we could, in such a scheme, imagine to reuse the existing GANIL infrastructure. So the recommendation 8 is to look at the possibility of post-acceleration of all the exotic nuclei produced at GANIL at intermediate energies between 10 and 100 MeV per nucleon. So now I move quickly to the last proposition, which is a bit farther, which is more prospective. And the idea is to use the electromagnetic probe to study the exotic nuclei. And this, of course, has been done already in the 70s or the 80s on the stable nuclei. And you can see that, for example, here you can really have a picture of the different orbitals in the exotic nuclei. So here it's a 3s valence orbital in lead 206, which has been obtained thanks to this diffusion of electron on this lead 206 and on tellurium, I think, 205. And this is possible simply because the electron penetrates deeply into the nucleus without absorption, and then, namely, the interior of the nucleus is accessible. Of course, this has been done in the 70s, as I said, on stable nuclei, but with unstable nuclei, almost everything is new. And then there are a lot of studies to really see what would be possible. So you have here a few numbers, and basically the idea is that you need what we call the luminosity, which is high enough in order to make physics. And of course, higher is the luminosity, more interesting is the physics you can do with such a luminosity. But of course, higher are the difficulties experimentally to get these numbers. So not really everything is new, because, for example, in Japan, at RIKEN, they have developed what is called the SCRIT technique, where the radioactive ions are trapped by the electron beam itself. So this is quite coherent with what will be available at DESIR. And then it means that, okay, there are already some idea of how we could do this kind of studies. So that's all for the development of our national installation. In the second part, the idea was to present some project of R&D, namely the reaction spectroscopy and the spectroscopy of fundamental nuclei. Of course, just giving some examples, because the idea was not to be exhaustive. So first, the idea was just to present the difference between the reaction spectroscopy and the decay spectroscopy for people who are not really familiar with that, but it's not the case of you guys today. So so you know that the idea is to send the beam on the target and to make a nuclear reaction and to detect around the target with the biggest efficiency and resolution all the products, neutron, gammas, light charged particle, and the heavy ions. And then, as you know, we put around the target different detectors which are dedicated to these different type of particles, which have also different energies. And then we need to develop different detectors, also depending if you are more interested by the efficiency or the resolution and so on. So, but you know all that, and the idea was also to say that most of these detectors that we have developed were developed within the framework of large international collaborations. And then, of course, if we do that in collaboration with people outside, it's natural to work outside of France, but also in France. And they have been supported by many appel à projet or funding calls, ANR and ERC. Also, I said that we have also alternative approaches. And I talk a little bit about the active targets, which have been basically developed for the first time in France with the Maya device. And now with ACTAR TPC, we have a very beautiful device which already produce very, very beautiful results. There is a Nature paper which has been published few weeks ago, for example. And again, to really say it once again, we have a very strong expertise at INTP3 to develop such detectors, and this gives us a very high visibility in international collaborations. So I will go very fast. You know all about this Agatha. So the idea is to have a gamma array with high efficiency and resolution. So the resolution, you have it by basically correcting for Doppler effect. So in order to do that, you need to know precisely where the first interaction took place, and then you need to have a tracking of your gamma. So and on this picture, just to show that the aim of the resolution is not only to get thinner peaks, as it is here when you compare VAMOS and Agatha and VAMOS hexagon, but also to be able to separate very tiny transitions which are otherwise not accessible. So you know all about the technological challenge, the high segmentation for the germanium crystal, all the pulse shape analysis procedure, full digital electronics, and so on. There are still ongoing developments to improve the existing capabilities. And then now the idea is to go from the phase 1, which was 1P, toward the second phase, which is, I think, 3 pi. And just to say that this detector has been already used very successfully, for example, in the last year at Ganil, for the last 6 years. You can see here some numbers which highlight really the high physics output which has been obtained with this detector. So the second example was with GRIT, which is also mandatory, because if you detect the gammas with a very high resolution, then you don't want to be limited by the resolution on the light ejectile. So you need also to detect the light particles which are emitted in coincidence with the gammas with a very high efficiency and with a detector with a high granularity. And then this is the idea why it was mandatory to develop something like GRIT. So the science driver, they are the same. And the technological challenge, they are in the fact that you want to use quite large detector and quite thick also. You have an issue with the packaging of all that. You should not make some, you should minimize the effect of the detector on the detection of the gammas with Agatha, for example. So there are ongoing developments. And concerning the status timeline, so the demonstrator of GRIT has been already successfully used with Agatha at Ganil in the last 2 years with many successful experiments. They will be used at Ganil again in 2023, 2024 at least. And the next is expected, for example, at space, and the full array is expected by the end of 2025. So just a few words about the last type of experiment, the stop beam experiments. As I said, the idea here is to make precision measurements, and contrary to the in-beam spectroscopy, here the aim is to develop a specific instrumentation dedicated to the measurement of a given observable most of the time. As I said, there are different type of experiments, decay spectroscopy, laser spectroscopy, trap-assisted spectroscopy. In the next 2 slides, I will give just few words about S-cube-Lab and PIPRAD. The idea is that the observables that we can measure with this method are mostly model independent, and saying that, in fact, they are quite complementary of what you can get with the reaction spectroscopy experiment. So both of them, they are really complementary. So I will go faster. So the S-cube-Lab, you all know about it. The aim is to provide pure radioactive beams, ion beams at low energy at the end of the S-cube spectrometer, and to perform medium resolution laser and mass spectroscopy for the N=Z nuclei and the super heavy elements. So to do so, it's based on the selective laser ionization method, which is done, and this is the technological challenge, it is done in a hypersonic flow. And by doing so, you can really improve the resolution of the laser spectroscopy in compare with what is done in a standard gas cell, where you have the ions in the gas which are thermally moving, and then you have a broadening of your spectra, and you can see here the gain in resolution you have when you make the laser ionization in the gas flow. So of course, to do that, you need also a series of RFQ in order to handle the beam and so on. You need also to develop an Emertov-MS spectrometer if you want to make mass measurements. So there are development right now ongoing at Ganil and at LPC. So there are developments, but also now they are entering in a test phase. Almost right now, they are already testing part of the setup. The test of the full setup is expected next year, I think with an erbium stable ion source. And the idea is to install it at S-cube in 2023 and the first experiment at the end of 2024. And the last example I gave was about the trap-assisted spectroscopy. So I presented this PIPRAD project that I suppose you know also. Here, the idea is to really get the highest selection for the exotic nuclei in order to be able to separate also isomers. So it means to separate masses of different nuclei with a few tenths of keV difference. So it means to have basically a mass resolution better than 10 to the 5. So this is done by using penning traps. Here the technological challenge with PIPRAD is to do and to get such a mass resolution, not by playing with few atoms at a time, as it is done when you want to measure a mass. But now you want really to select a bunch of nuclei, so you need to get this mass resolution, but for a large bunch of exotic nuclei. So of course you need a larger pinning traps and higher RF potentials and so on. So these are technological challenges that we manage to solve at Bordeaux, or we are in the process of doing it, since you can see here the first mass measurement, which has been performed, of course, on a stable nucleus a few weeks ago, and the mass resolution we obtained is already what we wanted. Of course, the number of nuclei is not yet the one we expect to have at the end, but the first steps are ongoing. And so the beamline is almost completed at CENBG, and now we are on the commissioning phase. And we are waiting for the Désir Hall to be able to put the system at Ganil. So just conclusion, on the left, you have a summary of what I presented, both for the development of our national installations and for the R&D projects. And the take-home message was that concerning the short-term period, we are ongoing. We are fully involved in the completion of the Spiral 2 phase 1, and the fast beam experiment program will be pursued at Ganil for the relevant topics and at international facilities. And for the midterm future, as I presented, we have different possibilities. The main one is, the first one, not the main, the first one is to provide fission fragments at Ganil, and for the longer term, the idea is to think about post-acceleration and collision of radioactive ions with a beam of electrons. So that was the end of the second part.